This is 6.4. We're going to do matrix addition and matrix subtraction. This does go with the handout. The first thing we want to talk about is a matrix and its size. We've already determined the notation where we have the brackets around a rectangular array of numbers or items or words. So we always designate rows with the letter M and columns with the letter N. So we can talk about the dimensions or the size of a matrix as an M by N. Think of area, length times width. So looking at this particular matrix, notice that you have 1, 2 rows, hence the 2, and then you have 1, 2, 3 columns, hence the 3 right here. So we have 2 rows, 2 vertical columns, and so that matrix dimensions or size is a 2 by 3 matrix. Okay, we can have what we call a row matrix. We can have a column matrix. A row matrix is just where we have 1 row. Column matrix is just 1 column. We can also have a square matrix, which has the same number of rows and columns. So we also need to be able to talk about the number of entries in a matrix, or excuse me, more like the number of elements. So if we talk about this number 2, this is the element, the first element in the first row and the first column. So the way we talk about that is 2 is in row 1. In fact, we would call it 2 is in row 1, column 1. So that looks like a subscript of 11, but it is not. This is row 1, column 1. So you think row by column. We just leave the little multiplications dot out of there. So when somebody talks about, say for instance, the element A13, it's not A13, it's A13. So we're looking at matrix A. This is how we've labeled it. So that means we're in the first row, third column. So that implies the number 4. In general, a lot of times you'll see them written as IJ. That's where we don't specifically know what row. It's a more general term, and J is the general term for column. So knowing that, then it's important now to know how to add and subtract matrices. Matrices is plural. Okay, we don't say matrices. So when we want to add one matrix to another, we simply add the corresponding units. So as you see right here, I will move on and I'll just actually do one. It is important to note that if the two matrices are not the same size, you cannot subtract, nor can you add them. So if we want to get the following sum, and yes, things can be done in your head, but I'm going to go ahead and show all the steps. So that's 5 plus negative 4, and then this sum gives me the element in the answer. So then I've got negative 6 plus 6. I've got 8 and 8, and then I've got 9 plus negative 3. I don't normally use double signs, but occasionally I do, and I tend to do that here so I can distinguish between add and subtract. So once then I do the arithmetic, I'll have a 1, a 16, a 0, and a 6. So this, people go, is this your answer? Yep, that's my answer. That is the sum of matrix. That is the result of adding those first two matrices. Notice that the dimensions, this is still a 2 by 2 or a square matrix. Okay, so let's add this one. What we need to notice is that we have a 2 by 2 and we have a 2 row by 3 column. Note that the dimensions are different, so we cannot add. It's impossible. Okay, so we want to find the following differences if possible. You do the same thing with subtract as you do with add. Notice that I have 3 rows and 2 columns. Notice over here that I have 3 rows and 2 columns. So since the dimensions match, I can certainly subtract those matrices. So I'm going to have 1 minus from the operation symbol, the negative 2, and then I'm going to have 0 minus 1. I'll have 2 minus 3, and I'll have negative 1 minus a negative 7, 3 minus 0, and 5 minus 2. So that my result, of course, subtracting a negative always results in a positive or an add. So that's going to be a 3, a negative 1, a 3, a negative 1, a 6, and a 3. So there's my answer. Notice it is also a 3 by 2 matrix. So in B, what we have are 2 row matrices. They're, let's see, not a 2. This is a 1 by 2, and this is a 1 by 2. 1 row, 2 column. So we can certainly subtract them. So what we'll have is 3 minus a negative 2, and then we'll have 5 minus 11. So that makes addition. So we've got then 5, negative 6. So there's your answer there. And then on this one, there's a square matrix, and that's a 2 by 2. This one is a 3 row, 1 column. The dimensions are different, so this one is impossible to subtract. Okay. All right, moving on. It is also important for us to be able to multiply by a scalar. A scalar is just a real number. We talk about that a lot of times in proportions and things like that. But a scalar is just a number that we use to multiply. It's a real number. So if I've got matrix A is 2, 3, 4, 5, 6, 7, and I want to multiply 6 times A, we put the 6 right here on the outside, and then every element gets multiplied by 6, and then your result is over here. It doesn't matter the dimensions. You can multiply any matrix, as far as I know of, by a scalar. So let's compute each one of these. So what I have is 12 times negative 2, 12 times 1. I'm just showing all the little gory details. And then 12 times 2. And then what we want to do then is perform that multiplication for each element. And we've got a negative 24, a 36, a 0, a 12, a negative 84, and 24. So there's my answer. That is the matrix that is a result of multiplying 12, the scalar, to this. Let's keep this in front of you. This is a 3 by 2 matrix. Okay, and notice my answer is exactly the same as far as dimensions. It's a 3 by 2. So here I have a square matrix. This is a 3 by 3, multiplying by a scalar. So my result should be a 3 by 3. So I'll have negative 3 times 1, negative 3 times negative 4, negative 3 times 0, negative 3 times 0. The question is always, Mrs. Burris, can I do this in my head? Of course. Whoops, that's a negative 3 times a 5. The thing you want to be careful of, though, is if you have a paper test where I'm grading partial credit and you miss an element and I don't see why you missed it, it's important to take these kinds of steps so that I can see that you know the process. So this is a negative 3, a 0, a negative 15, a 12, a negative 6, a 27, 0, 21, and 3. Notice we still have that 3 by 3. You don't have to tell me that. I just want to keep it before you. All right, here we have 3/5 multiplied by a row matrix. This is a 1 by 3 matrix. So I have 3/5, and yes, it can be a fraction. A fraction is a real number. And yes, you can have fractions appear as elements in a matrix. So I have 3/5. That's going to be 15/5 or 3, or just divide those out. And then this one is going to be 27/5. I'm not going to take the time to make that a mixed number. It's not relevant unless it's in an application problem that you're trying to work. So this would be your answer there. Okay, we can talk about a zero matrix. It's a matrix whose entries are all 0, something like this. Doesn't necessarily have to be square, but that is a zero matrix. And when we have one, if we're doing addition, it is the additive identity. Just like if I had 3 plus 0 and I would get 3, 0 is the additive identity, so this would be the additive identity matrix. We've got some properties just so that you're aware of with matrices. Matrices, this is matrix A plus matrix B is the same as matrix B plus matrix A. That means you can add those in any order you want. The associative property, as long as I have 3 matrices added together, I can add the first 2 matrices, then add that result to C, or I can group them in that I add B plus C, get that result, and add it to A. Provided they all have the same dimensions. That has to be the thing you look at. If I add a matrix to the 0 matrix or the identity matrix, that's how we write that. We get the matrix back, the original. If I add the additive inverse or take a matrix in one position and then its negative matrix in the other, I will get the identity matrix. And that order can be done. It's commutative. And then I've got the inverse property, whereas this is, you don't even have to think of it as a fancy property. You can think if I'm adding a negative matrix, it's the same here. I'm just subtracting the 2. So it's nothing to just, get all worried about. And that is the end of 6-4.